Work. Energy can be changed from one form to another. But can the amount of energy in a system be changed? Well, that depends on whether our system is closed or open. In a closed system, energy cannot be changed. In an open system, energy can be changed by applying an outside force outside the system that we're defining as an open system. But this force must be applied in a special way, and that way is work. Okay, here we bring in the open systems part here, where we have an external force acting on our system. Now, sometimes scientists take a regular word, like work, and give it a special meaning that doesn't match what you think it is. If you're holding up a heavy object, like the weightlifter down here, do you think you're working hard to hold it up? Of course you are. But in physics, if you don't change the energy of the object, you're not doing work. From a physics point of view, this athlete is not doing any work while she is holding the weights. In many situations, work can be found by calculating the change in energy of the system. Okay, we really don't have something called a workometer to do this. So we're going to deal with two forms of energy. One will be kinetic energy, which is the energy of motion, and two, gravitational potential energy, which is the storage of energy due to gravity. Work can either increase or decrease the energy in an open system. And we'll have a little sign convention here that positive work adds energy to your system, negative work removes energy. Let's put that in equation form. We have our initial energy in our open system plus work will equal final energy. So initial energy is written E sub I, work, capital W, not too surprising there, and final energy is E sub F. And then if we want to solve for work here with this equation, what do? We just subtract E sub I from both sides, and then we get work is E final minus E initial, and another name, anytime you have a final quantity minus an initial one, it's the change. And change, of course, is represented by delta. So work equals the change in energy. Changing the amount of energy in a closed system. If the system is closed, there is no work done on the system by outside forces, because the outside forces cannot act on the closed system. So work is equal to 0. That is, the initial energy of the system equals the final energy. Another way of saying that, the energy of the system doesn't change, and this is the conservation of energy. If the system is open and there are no outside forces acting on it, then the work also equals 0, and the mechanical energy is conserved. We'll talk more about this in the last topic of this presentation. Let's consider this airplane here on the deck of an aircraft carrier. Let's consider that an open system. And let's consider all these sailors who are pushing it, an outside force on the plane. How would you know if any work is done? Work is done on an object, and what do we need? We need an outside force, and it has to move the object to another position. These sailors only do work on the plane when they move it to a new position on the aircraft carrier's deck. As it moves, it has energy of motion, kinetic energy. If the plane doesn't move, its energy doesn't change, so what do we know about work? No work is done. Here's a very cool picture of a bunch of people just kind of balancing on each other, and it looks like a bicycle at the bottom. That's pretty cool. So if an object experiences a force and does not move, that means there is no displacement of the object, it's not moving. And if it's not moving, the energy isn't changing, so no work is done. And if you do have this force, since your net force is 0, there has to be an equal opposing force. When all that happens, we say that the object is in a state of equilibrium. Let's take an object of mass m, this one here, and let's say there's a force on it to the right, and it's actually moving to the right. The work in this case is positive. Work is greater than 0. So that happens when an object moves in the same direction as the direction of the net force. Acceleration will now occur due to the unbalanced force. And another definition of work is the ability to cause change. If an object moves in a direction opposite to the direction of the force, the work done is negative. The work is less than 0. So here we have an object moving in this direction, right? That's its distance that it's moving, that's its displacement. But there's a force going in the opposite direction. So this example is where you give a box a quick push along a tabletop and then you let it go. So that's going to get it moving. You know from experience that the box is going to stop at some point. Why is it doing that? Well, friction is a force opposing motion, and that's right here. The friction force and the direction of motion are opposite, so friction does negative work on the box. So we do have an acceleration due to the unbalanced force, but what's the direction of the acceleration? That way, it always matches the net force. So what's going on here is the box was moving with a certain speed after you pushed it, but it kept slowing down because the force was in the opposite direction of its motion. One more case. If the object moves perpendicular to the direction of the force, then the work done is 0. The energy of the object won't change. So if I've got this car moving in this direction, and let's say, well, you're in the car. You're pressing down on the car. Let's say you're not part of the car system. The normal force pushes you up. They balance out because you're not bouncing around in the car. Speed of the car isn't changing at all, is it? The energy is not changing, so no work is being done. And what we say here is no acceleration occurs. The speed isn't changing due to the fact that no component of the force, your force here, is acting in the direction of the displacement. And no work is done either by the normal force or the force of gravity. So we have 3 cases. Work greater than 0, the energy increases, your total mechanical energy increases. Work less than 0, energy decreases. And work equal to 0, energy stays the same. The amount of work performed depends on the sum of the outside forces and the displacement it moves in the same direction as the net force. And by the way, the further it moves, the more work has to be done to keep it moving. The work will be positive if in the same direction as the displacement, and negative if in the opposite direction. So we will have an equation that summarizes this. Work is the sum of the forces times the displacement in the parallel direction. It equals E sub F, final energy, minus E sub I, initial energy. Does this equation look familiar? It is very similar to our impulse momentum equation from the last unit. And we'll call this one the work-energy equation. Not terribly original. But here we have the work is equal to the sum of the forces times how far it moves is equal to the change in energy. The impulse momentum was the sum of the forces times time. We have a different variable there. And that will give us our change in momentum. So instead of time in the momentum equation, the energy equation has displacement. That basically repeats what I just said. And the energy equation is a scalar. Scalar. Energy is a scalar. It has no direction. And the momentum equation is a vector. It has direction. Since work is the change in energy, it must have the same unit as energy. Work is force times displacement. The unit of force is the Newton, and the unit of displacement is the meter. So the unit of both work and energy is the Newton meter, or written like this, N-M, or you can just write N space M, or N, put the M next to each other. In order to honor James Prescott Joule for his contributions to the understanding of energy, this is named the joule. Then you don't have to worry how to write Newton meter, you just write capital J for joule.